Okay, let's get started with the final session of the day. We're very happy to have Sucheta Majumdar tell us about Carroll theories from Lorentzian light connections.
Thank you very much for the invitation to give a talk here. And just in case you don't hear me well, just tell me, I'll try to fix the microphone. I'm going to talk about Carroll theories, which one can derive from these light cone field theories in Lorentzian spacetimes. Thankfully, we had some talks on flat space holography and Carrollian symmetries this morning and during the day. So I'm not going to tell you why Carrollian field theories are interesting. So that's, let's assume that Carrollian field theories are interesting. That's the first assumption for this talk. And I will start with, instead, with the different ways one can derive Carrollian field theories from any given theory. So let's say we know some Poincare invariant theory in d dimensions. We can get its Carrollian counterpart by taking the c goes to 0 limit. And there has been many works on this c goes to 0 limit of Poincare theories. There are too many people to name here, and as you can see, I gave up after some point. So, but for this talk particularly, I would like to bring your attention to this paper where Carrollian Hamiltonian actions were written down, and there they listed a set of necessary and sufficient conditions for any Hamiltonian theory to be Carrollian. And the theories that we will eventually derive from the light cone actions will satisfy these conditions. So they are, we can call them Carrollian theories. Secondly, we can derive Carrollian theories if we know the geometric objects on the Carrollian manifold itself, so the degenerate metric and the null vector and so on. And there's a third method where we start from one higher dimension in this special spacetimes called Bargmann spacetimes. And we can do some null reduction to get both Galilean and Carrollian theories. So here in the Poincare invariant case, if we took c goes to infinity limit, we get the non-relativistic Galilean field theories. And c goes to 0 is the Carrollian limit. Similarly, here there are two ways to get rid of this extra null direction. And one of these will get you to Carrollian spacetimes. So in this talk, we will use this null reduction method because the light cone Minkowski spacetime is a flat Bargmann manifold, as I will show you later. And when we do this kind of limiting procedures, we typically end up on one of the two Carroll sectors, electric or magnetic. In the electric case, the Hamiltonian density would involve pi's or time derivatives, so basically the velocities. The magnetic theory involves spatial gradients. So for instance, if I started with the Maxwell theory, where the Lagrangian is just E squared minus B squared, we would either get the electric part or the magnetic part. So now this talk is about deriving these kind of Carrollian theories from field theories in the light cone formulation. So let me tell you a bit about the light cone formulation. It is sort of an old subject where originally proposed by Dirac, where the idea is to formulate quantum field theories using a null time direction x plus, where these are the light cone coordinates. It's defined like this. And instead of taking x naught to be the time, one chooses x plus to be the time coordinate and develops the quantum field theory in this formulation. And there are some good reasons to do that. First of all, if you look at the stability group of this x plus equals 0, it is a 7-parameter subgroup of the 10-dimensional Poincare group in 4D. So it's the largest possible kinematic subgroup. So in case you're working with theories for which you do not know the interacting terms, for instance, high spin theories or supersymmetric theories, then this method is easier than the other choices of initial initial constant time hypersurface. Secondly, in the late 60s, it was noticed that some Feynman diagrams or loop computations in quantum field theories simplify tremendously when you work in this light cone or infinite momentum frame. And later, it was pointed out by Susskind that the reason for this is that there is a 3D Galilean subgroup within the Poincare, light cone Poincare algebra. One quick way to see this is just to look at the on-shell condition, p squared equals 0. And since x plus is the time, this Hamiltonian has a very non-relativistic expression, p squared by 2m. And indeed, this p minus also appears as a central extension, the mass in the algebra. And another reason is that in this framework, it is often easier to fix the gauge. For instance, in electromagnetism, we can choose A minus to be 0 and solve the gauge constraints and so on, and end up with a Lagrangian only in terms of the 2 degrees of freedom of the photon. And in the past, it has actually seen many successes in terms of loop computations in QCD or string quantization and so on. And in this talk, I will try to convince you that there is another reason, a fourth reason to think about light cone field theories, and that's the following reason. The reason is that we have several interesting kinematical subgroup, not just Galilei, but there are many more. And as a result, these light cone field theories exhibit both non-relativistic as well as ultra-relativistic features. So this is a brief outline of what I'm going to tell you about. I'll first start with the subgroups, and then how one can actually derive Carroll theories from relativistic light cone action. And depending on the kind of Carroll theories we get, we'll see there are some nice connections with the light cone formulation itself. Now, as I told you before, the light cone, the Minkowski spacetime in light cone coordinate, if you look at the metric, it has this form. And it is a flat Bargmann structure because you have 2 null vectors, this n and m, the del plus and del minus, which lie in the kernel of this metric. And as a result, there are actually 2 distinct Bargmann subgroups within the Poincare algebra. And within each Bargmann group, you have a Carroll and a Galilei subgroup and so on. So the gist of the story is that in a given d plus 1 dimensional Poincare algebra in the light cone coordinates, one has 2 copies of a d-dimensional Carroll, Bargmann, and Galilei algebra. And there is also a nice sort of duality between this x plus and x minus coordinates, because if you exchange the role of x plus and x minus, these subgroups map into one another. And this G plus group is the one that Susskind originally found. And the Carroll subgroups are actually the stability group of the light fronts at constant x plus or x minus. So basically, if we start with a Lorentzian light cone action and we are able to restrict it on one of the light fronts, we should be able to get a Carroll theory. So for this talk, I will consider x plus to be the Carrollian time, and we'll restrict the theories on constant x minus. And the relevant subgroup is going to be the B minus, which I showed you before. Now, before actually trying to derive the Carrollian theories, let me tell you some very general features of light cone field theory. When you look at, let's say, the scalar field action in this light cone coordinates and go to the Hamiltonian formulation, we immediately see that the conjugate momenta is actually not related to the velocities. And this leads to a primary second-class constraint in the theory, and this is very typical of light cone theories. And we also see that the canonical Hamiltonian only involves spatial gradient. Now, if you write down the light cone Hamiltonian action with this constraint through a Lagrange multiplier, it's going to look something like this. But as I said before, there is a second-class constraint which we can eliminate and which we can use to eliminate the pi's. And if we do that, then we go back to this action, because this is also first order in time. And this action is actually in the reduced phase space, where the non-trivial canonical pair now becomes phi at some space-time point x with phi of y, and they satisfy this sort of step function relation. Now, the idea is to restrict this theory on some constant x minus slice. So I'm going to constrain this x minus coordinate to some constant x minus 0 plus a very tiny width epsilon, and then later take this epsilon to 0. So it's simply by inserting some spearing function in the action. And we are going to assume some x minus behavior of the fields. So let's say at closer to x minus equals x minus x naught, the fields behave like this, and so on. And then we can simply get the Carrollian action by taking epsilon goes to 0 limit. And when we do this, we see that one only gets the magnetic Carroll action from the light cone Lorentzian action. And they do satisfy the nice properties that one needs for them to be Carrollian field theory. So they satisfy the correct hypersurface deformation algebra. They are invariant under this action is invariant under the Carroll transformations and so on. But there is no way to get an electric Carroll theory from simply restricting the Lorentzian action on the X minus hypersurface. So the question was, how do we fix this? And the fix is actually very simple. The problem with this original action is that it's too symmetric. It's symmetric under the full Poincaré group, which is sort of an overkill because we only need Bargmann invariance. So what I'm going to do is to add this term by hand, and then this term particularly breaks some invariance under some of the Lorentz generators, and we are only left with the Bargmann invariance of this subgroup. And now when we go to the Hamiltonian formulation, we see there are no second-class constraints in the theory anymore. And the canonical Hamiltonian has both pi's and spatial derivatives, so we do get both the electric and magnetic Carroll sectors. So for the magnetic part, we do the same game as before, and we get this magnetic theory. For the electric part, we rescale the fields a bit differently, and we get the electric theory. And we see that in this sector, the momenta are related to velocities, but in the electric Carroll sectors, in this sector, they are not related to velocities because there is no relation between these equations of motion. And here, we see that the momenta are actually time derivatives of the field. Now, we can do exactly the same thing for any P-form fields, for Minkowski, Yang-Mills, and so on. So more generally speaking, we just take the Lorentzian action and add this kind of a term by hand, and then we can get the electric and magnetic Carroll sector by taking the field strength. And here, for the magnetic Carroll sector, we only keep the F, I, J, K, L sort of components and kill the rest of the components. For the electric part, we keep the plus component of the field strength and kill off the rest. And then we get the correct electric and magnetic sector. So in summary, what we see, is it 5 or, oh, okay, great, thank you. We see that for the magnetic sector, we don't need to deform the action. We can simply start from a Lorentzian light cone action and do this sort of a truncation and get the correct magnetic Carroll theory in one lower dimension. But for the electric sector, we need to deform the action, and only then we get to the correct electric Carroll sector. So what is special about the magnetic Carroll part? So here we are going to claim that on flat backgrounds at least, the magnetic Carroll sector are consistent truncations of the Lorentzian theory. So for this, of course, both are consistent truncations, but for the Lorentzian case, it's only the magnetic Carroll part which is a consistent truncation. Now, we typically talk about consistent truncations in supergravity theories or Kaluza-Klein, where we do a dimensional reduction. Okay, so I was going to say this is where we try to find a link between the two. All right. So we typically think of consistent truncations in Kaluza-Klein theory. For instance, when we compactify one direction by some periodicity, and then we take the size of this extra dimension to be very small, we typically keep only the massless modes, and this gives us gives a low energy effective field theory description of the parent theory. So, but it really doesn't have to do anything with gravitational theories or anything. It's simply about the structure of equations of motion. So if we can find a solution of the truncated theory, which also solves the higher dimensional parent equation of motion, then it is said to be a consistent truncation. So in the context of light cone theories, what I mean is that if you look at the parent equation of motion, so this is the Lorentzian equation of motion, it's just box of phi equals 0. And we look at the Carroll equations of motion in one lower dimension, we see that if in the magnetic case, if this is true, then we can uplift the solution to one higher dimension by, and we can kill off the extra term. Just the magnetic part will also satisfy this, this higher dimensional parent equation of motion. But for the electric case, it's not a consistent truncation. Yeah.
You mean the So the magnetic theory also has another equation, right?
For the
For
momentum.
pi.
Yes. So I'm just coming to that in the next slide. Here I only show you one equation, and okay, let me just go to the next slide. So as you just said, that there are more equations. It's not just the field, but there is also the conjugate momenta. So how is this a consistent truncation? And if it is, then what does it describe in the Lorentzian theory? So if I worked with the off-shell Hamiltonian action, where we had the pi, the lambda, and this second class constraint, here I just show the electromagnetic action because you see there is a gauge constraint, the first class constraint, which generates the gauge symmetry, but even then there is always a second class constraint in light cone theories. But what we can do is to solve for this second class constraint and eliminate the pi's from the theories. And for Maxwell or gauge theories, we also set the light cone gauge conditions, A minus equals 0. So effectively, we can get a description of on-shell gauge fixed theories, which only involve this pi or AIs and so on. So the magnetic sector describes the effective, is an effective description of only this on-shell gauge fixed action. So it will not describe the solution space of this off-shell action, but only for the on-shell gauge fixed action, which is the so-called LC2 formulation, where we have only the physical degrees of freedom. So for that, you can take the magnetic solutions in one lower dimension and uplift them to the higher Lorentzian theory, but not for this action. And that is roughly what I wanted to say, but unless there is another question, okay. So yeah, as I said before, that in this light cone formulation, we have both relativistic and non-relativistic features, and we can try to see what kind of which of these features actually descend to Carrollian theories or Galilean theories and so on. And in the magnetic Carroll sector, we saw that we can describe the on-shell light cone phase space in one higher dimension using d-dimensional magnetic Carroll solutions, but not with the electric solutions. And whatever I said here is really about flat Bargman structure for curved geometries. This is generally not true because for curved geometries, the guess is that both the sectors can be consistently uplifted to the Lorentzian case, but one has to check that using a more general formulation, and also to see what happens for fermions and so on. But even in the flat case, this is actually a nice setup for some toy models. For instance, if I look at Carroll theories on intersecting light fronts, let's say I set up a Carroll field theory here and another one here. Just from the variational principle for the full system, we would need to have some matching conditions on the solutions here. We can also describe large gauge transformations or residual transformations of the symmetries of the parent theory in terms of gauge symmetries on these intersecting gauge symmetries of the Carroll theories on these intersecting light fronts and so on. And this point is a bit speculative here. What I wanted to say is that typically in the we see a lot of simplifications when we perform quantization in light cone formulation by putting it in a box. So it's called discrete light cone quantization, where the idea is to have some periodicity in the x minus direction. So we identify x minus with x minus plus L, and then take L to infinity. And this kind of quantization method helps regulate UV divergences. And here we are sort of doing the opposite limit. We are restricting x minus to some x minus x naught, x minus naught plus some epsilon, and then we take the epsilon to 0. So that, maybe this kind of Carrollian limit could be useful to understand IR divergences. And maybe what would be interesting to see as well is that what kind of properties or nice features of light cone quantization actually survive when we go to the Carrollian theories. And yeah, that's all I wanted to say. Thank you.
Questions?
Maybe I would like to comment that in the magnetic case, you can get from the magnetic case also the Galilean case. There are two pieces on the action, and one piece of the action will correspond to the Galilean case with central charge equal to 0.
Yeah, exactly. I think I went over it a bit too fast. There was a small comment that the fact that we only get the magnetic thing is also true for Galilean theories. When you get Galilean theories from Bargmann theories for flat backgrounds.
But what I'm saying is not necessary, because there is a mapping among Carroll and Galilean theories with central charge equal to 0, and you can see without enlarging the dimension. Essentially, in 1 + 1 dimensions is obvious, because if you change x by t, you pass from one to the other.
Exactly,
But in general, there's a relation.
Yeah, I agree with that, yeah.
If you remove the second-class constraints, then how many degrees of freedom do you have in the physical phase space?
You have sort of half the degrees of freedom, because you're removing the pi's from the theory. In the Hamiltonian phase space, typically we have pi's and phi's, but if you impose the second-class constraint strongly, you get half of it, because you're only...
But now you're removing that constraint, if I understand correctly, right? You said you don't...
yeah, in the Bargmann case, yes.
Right.
Yeah.
And then in that case...
No, I'm not removing the constraint. I'm saying the constraint is no longer there. So the pi's are not constrained anymore. They are now dynamical.
Right. So then, in total, how many degrees of freedom do you have in this case?
We still have so in the off-shell action, if I originally had, so in the off-shell action, we still have, wait a second. Here we still have pi and phi's. Only when I go on shell, when I impose the equation of motion for lambda, I will go to the reduced phase space. And I'm just making the pi's dynamical by hand. Yeah, thank you.
I have a question on the last point about the DLCQ.
Right.
So what do you expect to get a different insight on IR divergences than putting a cutoff and then removing the cutoff?
This is sort of like putting a cutoff, but then taking it to 0. But I don't know necessarily if this will give a different perspective or not. Maybe it will just tell us what we know in IR physics already. I
guess the difference is that you start with something that's periodic to begin with, rather than just putting a cutoff.
Exactly, yeah.
Okay. Other questions?
So in this periodic case, so I understand that you choose your light on time to be x plus.
Yeah.
But you could equivalently choose x minus,
Yes.
right? This is just the same.
Right.
So in this case, when you get periodic, isn't that similar to some kind of finite temperature situation? If you consider x minus to be your time?
If I choose x minus to be time?
Yes.
Sorry, what was the question?
If it corresponds to do something like a finite temperature field theory?
No, not necessarily, because I'm just flipping the role of x plus and x minus. It would be the same story. For finite temperature, you would need something more. Yeah. I mean.
If there are no more questions, let's thank Sucheta again.